All right, when we get started, so welcome to, oh, sorry, I forgot there was a session chair.
Hello, everyone. It's my honor to be the chair here. Thanks, Nat. So today we're going to have two session preview. One is about the synthesizer, and we have Nat Foster come from Canada University. So let's go.
Great.
Thank you.
Thank you. And just a note, I did not create this track so I could give a talk. I'm filling in for the speaker who sadly had a family emergency. So he was a real synthesis expert, but nevertheless, I didn't want there to be a hole in the program. So we're all familiar with program verification, or hopefully we're all familiar with program verification. And there's many different verification techniques. A lot of them depend on the style of semantics that's used, the kind of logic that you're using to describe programs, and the way you're relating those two. But fundamentally, the problem is, given a program and a spec, check whether the program satisfies the spec. And a lot of POPL is focused on that problem. Program synthesis turns this picture around. So instead of starting with a program, the idea is that we start with some kind of specification, and then we want to generate a program that satisfies it. And so you might have heard, synthesis is one of the sort of hot areas right now in programming languages, and there's, 2 whole sessions at POPL, and generally a lot of work going on in synthesis. But actually, one of the most highly cited and most downloaded POPL papers is by Pinelli and Rosner from '89, which would have fit in this year's POPL track on synthesis of a reactive module. So this actually is not a new idea. It has gotten a lot of sort of new momentum because of a lot of progress on automated theorem provers, SMT solvers, which are the engines of synthesis. They're the things that make it possible to do synthesis at scale. But the idea actually goes back quite a while and has been at POPL for ages. In fact, it even goes back to the 60s, right when people started designing finite automata. They immediately got interested in this question of, how could I generate automata from some higher level descriptions? So I want to give you just a very high level sort of perspective on what are some of the common challenges that arise in synthesis, and what are some of the techniques and approaches that the research community is taking to solve them. So, fundamentally, there's lots of different approaches to synthesis, but the big problem is, even once you fix the spec, there can be many programs that satisfy that spec, and along the way, there can be many programs that don't satisfy the spec or that can't be completed to the spec. So there's just this vast search space. And you need ways of somehow, filling in the detail in a specification to get a concrete program, while avoiding going down, long rabbit holes that end up being dead ends, or ending up with programs that either are suboptimal or don't satisfy the spec. So, the community has explored, again, lots of different approaches. One really simple one is what's sometimes called enumerative or top-down synthesis, where you're somehow starting from a space of maybe partial programs, and then you're filling them in sort of inductively as you go. And that's a very simple approach. Of course, the problem is that there can be lots of ways of filling in the holes. And there are other approaches as well. There are bottom-up approaches. There are approaches based on something called automata learning, and yet more. Another sort of common challenge, of course, is in any of these approaches, there's this vast search space, and there's different heuristics or approaches to navigating that search space. So a lot of systems, for example, will use a domain-specific language to impose structure on the search space. So instead of just generating sort of all programs in some general language, they'll say, here's a grammar, or here's a language that describes the set of programs I'm interested in for my domain. And then that helps guide the search because you're just looking for this smaller space of programs. And there are other things you can do as well. There's been recent work on using types, on using equations, or just plain old heuristics, metrics, and heuristics that work well. And then the third space where there's a lot of work is, and I guess DSLs also fit into this, but finding efficient abstractions as well as logical encodings. So there can be many ways to encode the specification, say, into a formula that can be often automatically checked. And people are also pushing the envelope in new domains where maybe SMT solvers may not be able to natively and quickly solve those formulas. So that's, again, a very high-level view of kind of what are some of the challenges in synthesis. And the papers in this session are quite diverse, although there's a couple of commonalities that I'll try to draw out. And I'm going to present them in a out of order because I want to kind of group them topically. So the second paper, which is the first one I'll present, is combining functional and automata synthesis to discover causal reactive programs. So the idea here is they're trying to do what humans do all the time, which is to construct what are called theories. A theory is not anything logical here. It's just a sort of way to understand, the world or a given domain. And they're interested in theories that respect certain kinds of causality, the kind of common sense causality that humans all learn. And so to do this, they're really combining two synthesis mechanisms. So they're using an approach for functional synthesis, where you can sort of think in a moment in time, they're figuring out the transfer function, for example, between two states of the program that they're generating, and using functional techniques for that. But then they also need to generalize. And so they're using some automata-based approaches to do the generalization and get the final program. And like some of the work I already highlighted, they introduce a new DSL that helps them capture causality so they can prune the search space, but also respect this desire to have causality. So I encourage you to come to this talk. The running example is based on a familiar video game, so they're interested in synthesizing sort of representations of a Mario-like game, and I'm sure the examples and graphics will be fun. So the next paper I want to cover, which is the first one in the session, is POPL', Learning Better Abstractions with eGraphs and Anti-Unification. Oh, and I should have said the authors. For the first paper, it's a group from MIT and Columbia and the Basis Research Institute and Stanford. The second group is a group from UW and San Diego, as well as Satora. So here, they're kind of down a couple levels. So they're interested in what's been called library learning. And so the idea is that you have a bunch of programs, and these programs come from some common class or domain. And you'd like to extract from them some reusable libraries of code. And perhaps these libraries would be useful building blocks for doing other synthesis tasks. So this is sort of a subroutine in a larger synthesis system. And one of the landmark papers that's mentioned quite a bit in this work, as well as one other paper, is Dreamcoder, a system from folks at MIT, as well as Kevin Ellis from Cornell, that does this. So it generates these libraries first and then does other kinds of synthesis on top of that. So the key idea here is they're doing this library learning, so given a bunch of programs, produce some library functions, and to help navigate the space, they allow the user to provide an equational theory. So you could, for example, say that this operation is commutative, and that could be used to guide the synthesis. And then also, to help navigate the very large search space, they're using eGraphs and equality saturation, which is a sort of set of technologies developed in the compiler domain, but is a very general approach to representing terms compactly and efficiently. And so they're using this to help drive their engine. And if you haven't seen eGraphs and equality saturation, they're really cool, and you can check it out. So this is sort of a nice use of them. So the third paper I want to cover, which is the fourth in the session, is also focused on library learning. And this paper does top-down synthesis. So think of starting with nothing and then starting to fill out a library of functions, et cetera, that somehow are match or extracted from the corpus of programs. So that's a very classic approach. The problem, as I already said, is trees grow large. So there's many possible libraries, and even if you're kind of filling it in top-down piecewise, you have lots of choices and lots of contradictions and dead ends. So they're using pattern matching and some other techniques to help prune the search space. And so I like this paper. The empirical results in this paper are amazing. So both the POPL' paper and this paper compare against Dreamcoder, which is itself a very impressive system. And they achieve orders of magnitude speed up. But this one really focuses on performance, and they get, I think it's 3 to 4 orders of magnitude speed up on the benchmark suites. So the approach here is, I won't call it simple because it's not, but it's sort of classic. But they've really kind of combined everything into a system that performs well. And then the third paper in the session, the last one I'll show you, is comparative synthesis, learning near optimal network designs by query. And it's by a group at Purdue. And so here, I guess one thing that's neat about this paper is it is applying synthesis in another domain. And so this is something that I love to see POPL papers do, because you're reaching out into another field and looking at their programming problems and seeing how you can bring them back in to our field and develop techniques. So specifically here, the kinds of programs they want to generate are network designs. So the topology of the network, where the links are, how much capacity should be on each link, maybe which routes are being used. And so this is a domain where systems folks care a lot about it. Different designs have different performance characteristics, have different costs. So there's a lot of interest in getting it right. And the problem is that the humans who are responsible for constructing these things, they don't have a spec. They might have some ideas about some of their objectives, but often their objectives are in conflict, or they need to make trade-offs. So this is not a case where you can just simply write down the spec for the network and get the design. So they have an interactive algorithm where they support some kinds of queries, and the idea is that the operators can basically sort of pose queries or provide interactive input. The tool goes off and starts generating a design. It gives them back one or more candidates. They can vote on those candidates or rank them, and then go back. So they're incorporating a human in the loop into the synthesis, and they have some quite nice results compared to prior work on network queries. So I'll stop there. Hope to see you tomorrow, unless, of course, you want to come to the semantics talk, which is also going to be excellent, 10:20 a.m. in the Grand Ballroom, too.